Ladies and gentlemen, esteemed guests, and distinguished colleagues, I extend a warm welcome to all of you to the Self-Paced International Symposium 2024, organized by JAL, Joint Asian African Labs, on this auspicious occasion of World Water Day. Today's session promises to be insightful and enriching as we delve into the fascinating world of spectroscopy and water analysis with our esteemed keynote speaker, Dr.K.Saminathan. Dr. Saminathan is a renowned scholar and an expert in the field of chemistry, particularly in areas such as physical chemistry, nanomaterials, colloids, electrochemistry, corrosion, and battery. Since joining Kongunadu Arts and Science College as an assistant professor in the chemistry department in 2016, Dr. Saminathan has made significant contributions to research and academia, earning accolades and recognition for his groundbreaking work. His journey in academia began with a strong foundation, as evidenced by his PhD in chemistry from Coimbatore University, where he delved deep into the subject and emerged as a proficient researcher. His doctoral thesis on sonochemical synthesis of iron oxide nanoparticles showcased his expertise and laid the groundwork for his future endeavors. Dr. Saminathan's passion for research is evident in his extensive publication record, with 13 research articles published in various reputed journals. These publications reflect not only his dedication to advancing scientific knowledge but also his ability to communicate complex ideas effectively to the broader scientific community. In addition to his research accomplishments, Dr. Saminathan has been recognized for his academic excellence through awards from prestigious agencies such as DST, Department of Science and Technology, UGC, University Grants Commission, and DBT, Department of Biotechnology, in India. These awards not only highlight his individual achievements but also serve as a testament to his commitment to excellence in education and research. Today's session on spectroscopy and water analysis is particularly timely and relevant, considering the global challenges we face in ensuring clean and sustainable water resources. Spectroscopy, with its ability to analyze the properties of matter based on interactions with electromagnetic radiation, plays a crucial role in understanding water composition, contaminants, and environmental impact. As we embark on this intellectual journey with Dr. Saminathan, I encourage all participants to actively engage in discussions, ask questions, and share insights. The exchange of ideas and collaboration among experts from diverse backgrounds is key to addressing complex water-related issues and fostering innovation in water analysis techniques. In conclusion, I extend my gratitude to Dr. Saminathan for graciously accepting our invitation to share his expertise and knowledge with us. I also thank all the participants, organizers, and sponsors for their contributions to making this symposium a success. Together, let us explore new frontiers in spectroscopy and water analysis for a sustainable and water-secure future. Thank you.
Good morning. I welcome you all for this JAL International Conference. I am Professor Saminathan from Department of Chemistry, Kongunadu Arts and Science College, Coimbatore. My topic is spectroscopic technique for water analysis. My topic covers introduction, benefits of spectroscopic techniques, application of water analysis, electromagnetic spectrum and Beers-Lambert's law, atomic absorption spectroscopy, flame emission spectroscopy, ICP-MS, and then heavy metal analysis and advances in AAS. So spectroscopy is a powerful technique. It analyzes chemical compositions based on the interaction between matter and electromagnetic radiation. Okay. So it ensures safety, quality, and easy to analysis. So benefits of spectroscopic technique is highly sensitive and selective. If you want to analyze copper, it will get the result for copper. If you want mercury, you will get mercury. If you want iron, you will get for iron. It is rapid analysis and the minimal sample requirement. So sample requirement is very minimal. Ability to analyze multiple elements simultaneously. If you put a sample with 10 number of elements, you can analyze with different calibration curves and a different analysis methods. That means you have to use specific lamp sources for specific element. Widely applicable across various water sources, types of contaminations, finding unknown chemical composition and materials. So benefits of application of water analysis: monitoring heavy metal contamination, accessing mineral content in the for drinking water, tracking change water composition over time. It can help in determining oil, grease contamination in large water sources. So normally for uh, port, that is the people handling lot of ships, it contaminates oil and greases, and um, for pharmaceutical industries, it is contaminated with lot of pollutants in the groundwater. So different type of industries have different type of pollutions. So, when we are going for spectroscopy, we cannot forget Beer-Lambert's law. It is a fundamental law. Another one, atomic absorption spectroscopy, flame photometry, and then inductively coupled plasma. These are the development. So flame photometry, atomic absorption is a basic spectroscopic technique which we employed in our chemistry lab. These are the electromagnetic spectrum. Electromagnetic spectrum from radio wave, microwave, infrared, visible light, ultraviolet, then X-ray and gamma rays. So this is the in center, it is in between visible spectrum. Okay, so these are the energy levels. So from the left side it is low energy, right side it is a high energy level. So in terms of electron volt, from you can see that's micro level, micro electron volt. In physics, chemistry, and whatever it is, you can. This is a Lambert's law. Lambert's law this first observation, an intensity of radiation passing through a fixed medium of that strength, whatever we are calling, called a fixed medium. Maybe the distance of the medium is fixed, and then intensity of the incident radiation measured. Then when we are passing that monochromatic radiation, that absorption on the liquid is proportional to the concentration of the solutions. We are taking 0.1 molar, the absorption is different. We are taking 0.2 molar. So that relationship is first explained by Lambert's. Then Beer-Lambert's law. Lambert's law. So he given that given little update to his the Lambert's law. Then it is combined as Beer-Lambert's law. So molar extension coefficient, molar concentration, they're coming with molar concept. Okay, this is a light source. So monochromator, it's a monochromator. Then incident light it fall in the cuvette, and transmitted light that is in the screen. So in the light source, this is the light source, the screen is our sensor. So it's a simple explanation of Beer-Lambert's law. Students can get it from Beers Lambert's law. Different type of animations are available. You can, if you want to study, if you want to study spectroscopy, first you have to read the Beers Lambert's law. Additive atomic absorption spectroscopy. Atomic absorption spectroscopy, we can estimate qualitative determination of chemical energy from elements by free atoms in the gaseous state. Atomic absorption spectroscopy is based on the absorption light by the metallic ion. AAS can be determined using around 60 to 70 different elements. We can calculate it from analysis from the solution phase. It is also measure the concentration of metals in the sample. So normally we will take a specific element, then it will be um, go for a calibration analysis, and then we will go for our unknown sample analysis. A is for basically functional atomic absorption built by Alan Wallace, CSIRO scientist in 19. This is a model of small instruments, radiation source, wavelength, detector, amplifier, signal. So this is one and where we will put it sample. Here we can put it for sample. Here it is an atomizer. This is a nebulizer is there. Then a nebulizer it will go to the atomizer. From the this is called analyzing zone. From this we can get it data. Okay. Instrumentation of atomic absorption. It is based on the principle that the gas is gas. What is that called? Carrier gas. It will carry the uh, uh, sample to the atomizer. That atomizer, that elements get atomized, then it absorbs the specific radiation with specific frequency. Based on the amount of absorption, the analyte concentration is freely dissociated in the ground state. Actually, it is when we are in the analyzing mode, it is getting to excited from ground state to excited state. It is going there. So, how much amount of energy it is observing from that, we will calculate the amount of it. Next, there are different types of lamps. That is the source we are using. So normally, hollow cathode lamp, HCl lamp. It will give only one element beacon. So one element for only one one lamp for only one element. A solution containing only introduced in the plane. Actually, hollow cathode lamp is highly sensitive. It will give you life of the lamp. The disadvantage is highly costly, and then it will can go for only one element per lamp. So this is a calibration curve, concentration versus absorption. This is a typical example curve for lead. This is our electronic readout detector, then monochromator. This is atomizer. This is analyzing zone. Okay. So what we will get it in the 3D. So the electronic readout it will go to computer, and then from that we can get it the XY data. So, and then we will go for Sometimes it will be connection RS-232 or USB, whatever it is connected to the computer to get the data acquisition. So ground state to excited state, and the element is going. So what we are observed from the value, we will get the calibration curve, and then unknown sample will be analyzed. This is a flame emission spectroscopy. It's almost simple. That is absorption spectroscopy. This compared with it is emission spectroscopy. So used for alkali and alkaline earth elements, we will use for this flame emission spectroscopy. Metallic salt solution introduced from the flame, and then it is evaporated from and the flame evaporated the solvent from the residue. It's almost like atomic absorption spectroscopy, but the thing is emission spectroscopy we will measure. This is a sample solution: air from the compressor, fuel and nebulizer, monochromator filter, and then lens, detector and recorder. Detector is compressor, recorder is a computerized part, detector is a instrumentation part. Okay, this comprises sample, nebulizer, burner, lens, monochromator, detector, and computer for internal for recording purpose. So working desolvation. The sample is mixed with the solvent in the sample. Then it is dehydrated in the flame, and it is solvents gets evaporated. Now only the metals are remaining in the flame. Then vaporizer. Then atomization. Then once it is excited, so the emission spectroscopy only we are measuring. Okay. From that it is absorption measurement data. This emission. Another one is ICP. ICP, inductively coupled plasma mass spectroscopy. Actually, what we are doing for that inductively coupled plasma is used. Inductively coupled plasma. So depending upon the heating source, we are using a plasma for this purpose, but a very minimum amount we can get it in the SP. But in that ICP technique, simultaneously we can measure 10 to 15 elements at a one single stretch. Why it is called intensively coupled or intensively coupled, inductively coupled plasma. The plasma source which is energy supplied from the electric current, which produce electromagnetic induction, that is by the time varying from the magnetic field. This is called ICP torch. That source is called ICP torch. Normally it is coupled with mass analyzer. Mass spectroscopy normally combined with ICP. So this diagram shows the generation of positively charged plasma. This is introduction of carbon to ICP. Aura field generated. So this is a basic instrumentation of ICP MS. The sample is introduced, then it is going for various stages. Quantitative analysis. Fundamental tool to analyze the concentration of unknown samples. Instrument is it should be calibrated by measuring the it should be calibration graph is must. Unknown samples are analyzed by plotting the measured intensities in the against the calibration curves. Now software calculates the concentration of unknown sample very easy. This is a typical example of example curve of example instrumentation of ICP MS. Heavy metal analysis. So heavy metal analysis are toxic, potentially harmful to our human bodies. Heavy metals are defined as metallic elements are relatively high density compared to water. The heavy metals are safe in very small amount. Otherwise, it will go very harmful. So, example: mercury, lead, chromium, cadmium. Okay, these are the side effect of heavy metal ions. Arsenic, internal cancer; cadmium, cancer; copper, that will also into Alzheimer; chromium, that's ulcer, skin irritation; lead, spontaneous absorption, nervous system damage; mercury, memory problem. Analysis of heavy metal ions. Analysis of heavy metal. It's normally in atomic absorption spectroscopy. We use for mercury analysis by FIAS techniques, flow injection analysis system. So heavy metals can now easily can be analyzed with the help of X-ray. It's immediate non-destructive techniques. These are the simple instrumentation of X-ray analysis. So XRF. XRF is another one technique. So we can easily calculate the samples, but it should be solid. Okay, liquids it is not easy, but solid it can be managed within 10 minutes. We can get SRF, X-ray, fluorescence. This is instrumentation. X-ray, fluorescence instrumentation. I hope I explained various spectroscopic technique. A simple spectroscopic technique, whatever techniques are available for simple understanding for students, so that they can get into that system, use the spectroscopic method effectively for their water analysis.